Hello, I would like to cover Introduction to Neutron Scattering, the NCNR, talk about neutron sources, then continuous versus time of flight, and then introduce the NIST neutron scattering facilities, interactions, say something about elastic and inelastic neutron scattering, and then coherent and incoherent. Then finally, introduce scattering length and contrast factors before getting into science. Why use neutrons? They're very penetrating and do not destroy samples. Neutron wavelengths are comparable to atomic sizes interdistance spacing, making neutron scattering very useful for determination of atomic structures. Neutron interaction with hydrogen and deuterium are very different, making the deuterium labeling method a big advantage. We'll say something about that. Neutron sources. The main one is fission chain reaction in the nuclear reactor. Instant neutrons is absorbed in a fissile nucleus like uranium-235, plutonium-239. There is a fission nuclear reaction that takes place, two fission fragments, 2 or 3 neutrons, which when they get slowed down in water, in the moderator, they give more and more fission reactions. That's a nuclear reactor. The second neutron source, type of neutron source, spallation nuclear reaction, where a proton is incident on a very heavy high Z nucleus like tungsten or uranium-38, gives off 10 to 30 neutrons, which when slowed down, they can be used for neutron scattering. Continuous versus time of flight. Continuous reactors, where there is a monochromator and pulse in pulse sources, there is a chopper. So in a continuous method, we choose one wavelength out of the white beam coming out of the source, and the neutrons are constant coming out of the source as well as at the detector. We use some of the neutrons all of the time. We use only one wavelength, some of the neutrons all of the time. While in pulse sources, one uses a chopper, so you get these pulses coming from the neutron source. By the time they get to the detector, they're spread out, depending whether they're fast or slow within the pulse. So we measure all of the wavelength, all of the neutrons, some of the time. Neutron sources in the US, there are 2 nuclear reactors, one at Haifa, Oak Ridge, and one here at NIST, and 2 pulse sources, one at Los Alamos and one the spallation neutron source at Oak Ridge as well. The NIST neutron source, I'd like to show you instruments inside the confinement building. These are thermal instruments, and then there is a cold source, which is liquid hydrogen. And then this cold source produces cold neutrons with low kinetic energies, in other words, long wavelengths. And a bunch of guys that look at this cold source, the old guide hall and new guide hall, as I will show. Upgrade and VSENS, this is the old guide hall, this is a new guide hall. There is a thermal USENS instrument included in this summer school. I'll say something about it. And there are 2 30-meter SENS, the NG7 and the NG3, which just got moved to the new guide hall. The old 10-meter SENS, and then we're building a VSENS, 40-meter VSENS, high-resolution instrument. The NIST guide hall, the old one, there's the NG3, the NG7. There's the NG3, just got moved last week actually. And then there's the new guide hall Old guide hole is there. The new guide hole, there's a 10-meter SANS. The NG3 SANS going to be installed here. Neutron interactions. X-rays interact with electron cloud. So scattering increases with the atomic number, while neutrons interact with the nuclei. So it's almost random. So you see the scattering length changes from one element to the other. Like for example, hydrogen has a negative scattering length, while deuterium has a positive scattering length. They are different, and so on and so forth. Elastic versus inelastic neutron scattering. So during a scattering event, there is transfer of momentum and transfer of energy. Think of momentum as the scattering angle, the energy as the kinetic energy of the neutron. Neutrons lose energy or gain energy. I'd like to say that elastic scattering corresponds to a transfer of energy around zero to investigate the structures. SANS and neutron reflectometry are elastic scattering techniques. So I'll show you the momentum and energy transfer window, all of the instruments that we have. And since this is almost like in Fourier space, the inverse Fourier transform is length inside the sample. The inverse Fourier transform to energy is time scale for the dynamics inside the sample. And you get the length scales, for example, between 1 angstrom and 1,000 angstroms, and the time scales are between 10 to the minus 13, 10 to the minus 7 seconds here. I'd like to say that SANS and reflectometry, as well as diffraction, are elastic techniques. In other words, no energy transfer around zero. Scattering length densities. Usually you start by checking out scattering length densities of your system that you're going to measure with neutron scattering. There's a calculator on the web. An example, like to find out scattering length density for heavy water, D2O. There's a density around 1.11 gram per ml. Output, find scattering length density of 6.39 10 to the minus 6 inverse angstrom squared. Please remember the order of magnitude and the units. The scattering length density is the ratio of the scattering length divided by the volume. For example, for a molecule, you sum up scattering length for all of the atoms and divide by the volume of that molecule. For a micelle, the same thing. For a monomer, the same thing, scattering length density. Summation is done in the scattering length calculator. Contrast match method, showing you a finite contrast, like blue particles in a white background. Zero contrast when the solvent, for example, matches the particles, same scattering that you would not see anything, just flat scattering. The case of multiple contrasts, you could play the contrast match game by contrast matching, for example, solvent to the blue particles. All you will see will be the red particles. I think you got the gist of it. This is the main advantage of neutron scattering over X-ray scattering. Well, one of the advantages. I'd like to show you SANS geometry. Typical instrument. This figure is not to scale. This is 2.5 centimeter radius for the source aperture. Half inch, 1.27 radius for the sample aperture. This is 15 and 15 meters. So the minimum angle that you could measure reliably, which gives you the minimum scattering variable, is given here, is the ratio of R1 plus R2 over L1 and so on. And in this case, 15 and 15 meter and so on, turned out to be 0.2 degrees. How small are small angles? There you go. The low Q configuration starts at 0.2 degrees. Then you can go up to 2 degrees for low Q. for high Q configuration from 2 degrees to 20 degrees. That gives you a order of magnitude of the angles involved in small angle neutron scattering. I'd like to say something about reflectometry geometry. I took the previous slide, the previous schematics, and collapsed everything by a factor of 10. Instead of 15 meters, I have 1.5 meter. Instead of 2.5 centimeter, I have 2.5 millimeter. Instead of transmission, I have reflection geometry. So in other words, instead of circular apertures, we have slits here. Okay? Guess what? The ratios do not change. R1 plus R2 divided by L1. This is divided by 10, divided by 10. The ratio doesn't change. So in other words, reflectometry involves the same type of angles, scattering angles, even though reflectometers are 10 times smaller than SANS instruments, just because using very tight slits and so on. Okay.